Imagine for a moment the profound silence of deep space, a vast, empty expanse where our farthest emissary, the Voyager probe, journeyed for decades, carrying with it the hopes and curiosity of all humanity. Then, without warning, something extraordinary happened. In its final transmissions before contact was lost forever, Voyager recorded readings that defied every known law of physics. A strange, inexplicable anti-gravity anomaly, an invisible force that bent space itself. This wasn't just another cosmic mystery. It was a signal from the edge of the known universe, a whisper of something beyond our understanding, hidden in the data of our most intrepid explorer. What did Voyager truly encounter in those final moments? Was it a natural phenomenon unlike anything we've ever witnessed, or could it have been something far more profound, a clue to forces that reshape our very conception of reality? This isn't just a story about data and sensors. It's about humanity reaching out into the cosmos and touching something inexplicable, something that challenges everything we thought we knew. The anomaly remains one of space exploration's greatest unsolved puzzles, a tantalizing secret waiting at the boundary between our world and the infinite unknown. Join us on a journey to the very frontiers of discovery, where science meets mystery and the lines between the possible and the impossible blur. Together, we'll explore the thrilling evidence, the compelling theories, and the breathtaking implications of what Voyager found, or perhaps what found Voyager, in those final, fleeting moments of contact. This is more than a mystery. It's an invitation to wonder, to question, and to imagine what might lie waiting in the depths of space just beyond our sight. To understand the significance of those final, mysterious signals, we first need to appreciate the incredible machine that sent them. The Voyager mission stands as one of humanity's most ambitious and triumphant voyages of discovery. Conceived in the 1960s and launched in the late 1970s, the program consisted of two identical, car-sized probes, Voyager 1 and Voyager 2. Their primary mission was an epic grand tour of the outer solar system, a rare planetary alignment that allowed them to visit Jupiter, Saturn, Uranus, and Neptune, using the gravity of each planet as a slingshot to propel them onward to the next. These were not simple flybys. Each encounter was a revolution. Voyager revealed active volcanoes on Jupiter's moon Io, the intricate, dazzling rings of Saturn, the bizarre sideways tilt of Uranus, and the supersonic winds of Neptune. They transformed these distant points of light in our telescopes into complex, dynamic worlds, forever changing our textbooks and our understanding of our cosmic neighborhood. But their journey was far from over after the planetary tour. Having completed their primary objectives with resounding success, the twin probes embarked on a secondary mission of profound importance to venture into the void. Their new goal was to reach the very edge of the sun's influence, a boundary known as the heliopause, and then to become the first human-made objects to enter the space between the stars' interstellar space. Powered by radioactive thermoelectric generators, they were designed to keep going, to keep communicating, long after they left the planets behind. For decades, they sailed through this distant, silent realm, dutifully sending back data on the magnetic fields, cosmic rays, and the properties of the solar wind as it dwindled away. They were our scouts, our mechanical pioneers, carrying with them the famous Golden Records phonograph records containing sounds and images selected to portray the diversity of life and culture on Earth, a message in a bottle for any intelligence that might one day find them. Yet as these robotic ambassadors sailed further into the void, they carried more than just scientific instruments. They carried a piece of humanity itself. Mounted to each probe's side is a 12-inch gold-plated copper disc, a literal golden record, designed to survive for 1 billion years in the harsh environment of space. This was not a casual addition. It was a profound statement, a deliberate message cast into the cosmic ocean. Conceived by a committee led by the visionary astronomer Carl Sagan, the record's purpose was monumental: to tell the story of our world to any intelligence that might one day intercept the silent, drifting probe. It is a time capsule of humanity, a carefully curated collection of sounds, images, and music intended to depict the diversity of life and culture on Earth. Imagine the hope and optimism required to create such a thing, the belief that something of our essence, our art, and our spirit was worth preserving and sending on a one-way trip to the stars, long after everyone involved in its creation had passed away. The contents of this record are a breathtaking snapshot of our planet. Etched onto its surface are 115 analog images, ranging from mathematical and scientific definitions to photographs of human anatomy, our DNA structure, and the planets of our solar system. It shows scenes of everyday life, people eating, laughing, working, and learning. There are landscapes from across the globe, from the snow-capped peaks of the Himalayas to the sandy shores of a beach, revealing the stunning beauty of our home. But perhaps even more powerful are the sounds. The record contains an audio essay of Earth's natural symphony: the crashing of ocean waves, the patter of rain, the rumble of thunder, the songs of birds and whales, and even the frantic heartbeat of a human being. Then there are spoken greetings in 55 ancient and modern languages, from Akkadian, spoken in Mesopotamia thousands of years ago, to modern English, each voice offering a simple hello from the people of Earth. The record also includes a written message from then-President Jimmy Carter, who spoke of humanity's hopes to one day join a community of galactic civilizations. And then there is the music. This is perhaps the most soulful part of the message. The selection is a global concert, a carefully chosen repertoire designed to represent the entire human experience through melody and rhythm. It includes everything from the soaring precision of Bach and the fiery passion of Beethoven to the blues of Louis Armstrong and the rock and roll of Chuck Berry. There is traditional music from across the continents: a Navajo night chant, a Peruvian wedding song, Senegalese percussion, and a shakuhachi flute piece from Japan. Each track was selected to communicate emotion, creativity, and intelligence in a universal language that transcends words. This musical mosaic represents our deepest attempts to express joy, sorrow, wonder, and love, the fundamental emotions that bind all of humanity together. The very existence of the Golden Record is a testament to an audacious and hopeful vision of the future. It represents a moment in time when we looked beyond our earthly conflicts and dared to imagine a conversation with the cosmos. It asks a fundamental question, not just about who might be out there, but about who we are. What would we want another intelligence to know about us? The answer, crafted by Sagan and his team, was one of peace, curiosity, and celebration. They chose to highlight our intellectual achievements, our artistic beauty, and the rich tapestry of life on our fragile world. It is a message of friendship from a species still in its infancy, cast adrift with no guarantee it will ever be found. Long after Voyager's nuclear heart grows cold and its instruments fall forever silent, this golden phonograph record will continue its endless journey, a silent testament to a civilization that once looked up at the stars and dared to say, "We are here." Having triumphantly completed its grand tour of the planets, Voyager 1's mission was far from over. Its nuclear power source still provided a trickle of energy, and its ancient computers, with less processing power than a modern car key, continued to function flawlessly. This granted the probe a new, profound purpose: to become humanity's first interstellar ambassador, to push past the final frontier of our sun's influence and report back from the great unknown. Its final scientific objective was to find and characterize a boundary that, until that point, had only existed in theory: the heliopause. This is the outer edge of the heliosphere, a vast protective bubble created by the solar wind, the constant stream of charged particles billowing out from our sun. Think of the heliosphere as a kind of cosmic weather shield, deflecting a portion of the dangerous galactic cosmic rays that permeate interstellar space. For billions of miles, this solar wind is the dominant force, carving out a cavity in the galaxy. But nothing lasts forever, not even the sun's reach. The heliopause is the point where the outward pressure of the solar wind finally equals the inward pressure of the interstellar medium, the gas, dust, and cosmic rays that fill the space between stars. It is the ultimate shoreline where the tide of our solar system meets the ocean of the galaxy. For years, scientists on Earth watched the data stream in, waiting for the telltale signs that Voyager was approaching this mysterious border. They monitored the velocity and density of the solar wind particles, expecting them to slow down and eventually stop as the probe encountered the resistance of interstellar space. Then, in the summer of 2012, after a 35-year journey covering over 11 billion miles, the readings on Earth began to change dramatically. The sensors designed to count solar wind particles recorded a sudden and precipitous drop. The particles that had been a constant companion for decades, the very signature of our sun's influence, nearly vanished. At the same time, instruments measuring galactic cosmic rays high-energy particles from outside our solar system showed a sharp increase. It was as if Voyager had sailed through an invisible wall, leaving the protective bubble of the heliosphere and entering the open waters of the galactic sea. After months of intense analysis to confirm the data, NASA made the historic announcement. On August 25, 2012, Voyager 1 had officially become the first human-made object to enter interstellar space. This was a monumental achievement, a milestone for our species on par with leaving Earth's atmosphere for the first time. But Voyager's work was not done. Its task was now to characterize this new environment, to be our eyes and ears in a realm no object from Earth had ever touched. It continued to send back priceless data on the magnetic field direction, the density of the plasma, and the intensity of cosmic rays. For the first time, we could study the stuff between the stars directly. Scientists learned that the interstellar medium is far denser than previously predicted, and the magnetic field just outside our solar bubble is significantly stronger. Each bit of data was a revelation, refining our models of the galaxy's structure and our place within it. Voyager was mapping the final frontier, its faint signal, now taking over 17 hours to travel at the speed of light to reach Earth, whispering secrets from the void. This was the apex of its mission, the brilliant, data-rich climax of a journey decades in the making. It had achieved its ultimate goal, and its legacy as the farthest-reaching and most successful probe in history was forever secured. Yet, this crowning moment of discovery was also the prelude to its most baffling and unexplained encounter. For nearly a decade after crossing into interstellar space, Voyager 1 performed flawlessly, its data stream a steady heartbeat from the void that scientists monitored with quiet pride. Then, in 2022, that steady rhythm began to stutter. At first, the changes were subtle, barely a flicker in the torrent of numbers flowing into NASA's deep space network. But soon, they became impossible to ignore. The probe's plasma wave subsystem, designed to measure the density of ionized gas in space, began registering wild, impossible fluctuations. Instead of the consistent, low hum of the interstellar medium, the readings spiked and plummeted erratically, as if the probe were moving through invisible cosmic waves that had no business existing in that region of space. Simultaneously, the magnetometer's instruments that have been mapping magnetic fields since the probe's encounter with Jupiter started reporting a similar story of chaos. The magnetic field strength, which had stabilized after crossing the heliopause, began to oscillate in a bizarre, unpredictable pattern that defied every model of interstellar physics. The initial reaction among the veteran engineers and scientists at the Jet Propulsion Laboratory was not one of excitement, but of profound confusion tinged with concern. Their first assumption, born from decades of managing an aging spacecraft, was a hardware glitch. Voyager 1 is, after all, a marvel of 1970s engineering, running on computers with a fraction of the memory of a modern calculator. It has overcome countless technical issues over the years, each one painstakingly diagnosed and fixed from over 14 billion miles away. Teams began the meticulous process of sending diagnostic commands, checking for corrupted memory, faulty circuitry, or any other sign of instrument failure. But every diagnostic check came back green. The hardware was functioning within normal parameters. The impossible data wasn't coming from a broken machine. It was being generated by instruments that were, by all accounts, working perfectly. This was the moment the mystery truly deepened, shifting from a potential technical problem to a potential cosmic one. As the weeks turned into months, the anomalous signals did not disappear or resolve themselves. Instead, they evolved. The data formed a strange, complex pattern that seemed to tease the scientists, suggesting an order just beyond their comprehension. It was nothing like the clean, predictable data from a planetary flyby or even the historic crossing of the heliopause. This was something entirely new, a signal without a clear source. The readings suggested the presence of a localized region where the very fabric of space seemed to behave differently. A pocket where the influence of gravity appeared to be weakened or perhaps even negated. The plasma wave data, in particular, hinted at a phenomenon that could be interpreted as an anti-gravity effect, a concept straight out of theoretical physics that had never been observed in nature. The team found themselves staring at printouts and screens, faced with a reality that their textbooks and decades of experience had not prepared them for. They were no longer just listening to the whispers of interstellar space. They were listening to it speak in a language they did not yet understand. This bizarre gravitational anomaly, this so-called anti-gravity effect detected in Voyager's final data, demands a closer look to separate science fact from science fiction. When we hear the term anti-gravity, our minds might leap to floating cars or tractor beams from our favorite space operas. But in the sober, data-driven world of astrophysics, it signifies something far more specific and startling. It refers to a region of space where the gravitational force behaves in a manner completely opposite to everything described by Isaac Newton and Albert Einstein. Instead of the familiar, relentless pull that keeps planets in orbit and our feet on the ground, the readings suggested a force that was inconceivably pushing back. To grasp this, we need to think of gravity not as a simple force, but as a curvature in the fabric of space-time itself. Imagine the universe as a vast, taut rubber sheet. A massive object like a star creates a deep well in that sheet, and smaller objects naturally roll down the slope towards the center. This is gravity as we know it. What Voyager's instruments seemed to detect was the equivalent of an invisible hill on that cosmic rubber sheet, a region where the fabric of spacetime itself bulged outward, creating a repulsive effect that would push objects away rather than pull them in. This isn't about canceling gravity with some kind of technology. It's about a natural yet profoundly strange geometric property of space itself in that specific location. The data pointed towards a localized pocket, a cosmic bubble where the fundamental rules were temporarily suspended or rewritten. The probe's trajectory, monitored with incredible precision over decades, showed minuscule but measurable deviations, a slight nudge that couldn't be explained by the gravitational influence of any known celestial body. Furthermore, its instruments measuring the density and flow of interstellar particles recorded a strange void, a region of unnaturally calm and empty space surrounded by the turbulent interstellar medium. It was as if Voyager had briefly sailed through an invisible bubble, a pocket of nothingness that exerted a faint but undeniable push against the probe and everything around it. This anomaly wasn't a powerful force hurtling the probe across the galaxy. It was a subtle, pervasive whisper of repulsion, a signature of physics operating under rules we have yet to discover. Faced with such bewildering information, the seasoned team at the Jet Propulsion Laboratory did what any good scientists would do. They immediately looked for the simplest, most logical explanation. Their decades of experience had taught them that extraordinary claims require extraordinary evidence, and their first responsibility was to rule out the mundane. The most plausible hypothesis was not a cosmic anomaly, but a final, quiet farewell from the probe itself. After all, Voyager 1 is a marvel of aging technology, having operated in the vacuum of space for over 45 years, subjected to extreme temperature swings and constant bombardment by cosmic radiation. It was entirely reasonable to suspect that these bizarre readings were not a message from the universe, but the last gasps of a dying machine. The investigation into a potential instrument glitch was a massive, meticulous undertaking. Engineers began by sending a series of complex diagnostic commands across the 14.6 billion miles separating Earth from the probe. Each command took over 22 hours to reach Voyager and another 22 hours for the response to travel back. This was a painstaking process of waiting and analyzing. The team focused their attention on the two primary instruments reporting the anomaly, the plasma wave subsystem and the magnetometers. They ran deep-level memory checks looking for corrupted bits of data that could be causing the instruments to miscalculate and output nonsense. They tested the voltage levels to the sensors, searching for any sign of a power fluctuation that could create electrical noise and distort the readings. They even compared the data against the backup systems, though many of those had been powered down years earlier to conserve the probe's dwindling nuclear fuel. Yet, after weeks of this intensive analysis, the results were not what anyone expected. Every diagnostic report came back indicating nominal health. The memory was clean. The power levels were stable and within expected tolerances. The circuitry, as much as they could test it from such a distance, showed no signs of critical failure. The instruments themselves were stubbornly reporting that they were functioning perfectly. This presented the team with a deeply unsettling paradox. The data was telling them something impossible was happening in space, while simultaneously telling them that the tools collecting that data were in perfect working order. It was as if a perfectly healthy and sober person was consistently reporting they were seeing flying elephants. You trust the person, but you cannot believe what they are saying. This led the engineers down a more nuanced path of investigation. Could it be a software glitch rather than a hardware one? The probe's computers run on archaic code, and perhaps a cosmic ray had flipped a critical bit, causing the algorithms that interpret raw sensor data to malfunction. The team began reviewing the foundational calibration software, the complex set of instructions that translates electrical signals from the sensors into the numerical data that gets beamed back to Earth. They searched for any flaw in the logic, any place where the math could go astray and produce a false positive for such a strange phenomenon. Again, they found nothing. The calibration tables were correct, the mathematical formulas were sound. The software was doing exactly what it was designed to do, which was to faithfully report what the hardware was detecting. The inability to find a glitch forced a profound shift in perspective within the mission control team. The initial hypothesis, the safe and comfortable explanation of a failing machine, was crumbling under the weight of contradictory evidence. With each passing day and each clean bill of health from the probe, the once implausible idea that the signal was real gained more traction. The engineers, masters of logic and machinery, found themselves reluctantly considering that their 45-year-old creation had not broken down at all. Instead, it had faithfully done its job one last time, stumbling into a region of space so strange that it defied their models and challenged their understanding of physics itself. The very normality of the spacecraft systems was becoming the most abnormal and thrilling data point of all, with the possibility of a technical malfunction looking increasingly unlikely. The team at Mission Control was forced to turn their attention to a far more thrilling and unsettling explanation. What if Voyager's instruments were not lying? What if the probe, in its endless drift, had truly encountered something unprecedented, a previously unknown property of spacetime itself at the very frontier of our solar influence? This line of thinking opened the door to a realm of speculation that was equal parts exhilarating and humbling, suggesting that our map of the universe still contained vast, uncharted territories. One of the most compelling theories proposed by the science team involved the concept of quantum foam. At the very smallest scales theorized by physicists, the vacuum of space is not truly empty or smooth. Instead, it is believed to be a seething, chaotic froth where particles and energy flicker in and out of existence in a probabilistic dance governed by quantum mechanics. Under normal circumstances, this underlying turbulence is invisible to us, its effects too minute to measure. However, some scientists speculated that at the boundary of the heliosphere, where the sun's magnetic influence wanes and the raw interstellar medium takes over, this quantum foam might become more pronounced. It's possible that Voyager sailed through a region where the very fabric of reality was more turbulent, a cosmic rapids where the subtle rules of quantum gravity created minute-detectable fluctuations that registered as a strange push or pull on the probe's sensors. This wouldn't be a massive anti-gravity engine, but rather the faint background hiss of the universe's underlying structure, finally loud enough for our instruments to hear. Another fascinating hypothesis points toward dark matter. We know this mysterious, invisible substance makes up the majority of the matter in the universe, binding galaxies together with its gravitational influence. Yet, despite its prevalence, we have never directly detected a single particle of it. We only infer its existence from its gravitational effects on visible matter. What if the Voyager probe, by sheer chance, ventured through a localized, dense clump or a strange topological defect in the dark matter halo that surrounds our galaxy? The gravitational influence of such a concentration could potentially warp local space-time in ways that don't align with our models based on visible matter alone, creating the anomalous readings. Voyager wouldn't have found dark matter in the traditional sense, but its sensors might have recorded the indirect gravitational ripples of its unusual structure, a ghostly fingerprint left on the instruments. Perhaps the most mind-bending theory involves the very nature of gravity. Einstein's theory of general relativity has been spectacularly successful for over a century, predicting everything from the orbit of Mercury to the existence of black holes. But it has never been perfectly unified with the other fundamental force of nature, quantum mechanics. Many physicists believe a more complete theory of quantum gravity must exist, one that describes how gravity works at the smallest scales. It's possible that at the extreme edge of our solar system, in the near-total emptiness of interstellar space, Voyager encountered a set of conditions where the subtle differences between Einstein's relativity and a truer theory of quantum gravity became marginally detectable. The anomaly could represent a tiny crack in our understanding, a place where the universe itself is hinting at a deeper set of rules that we have not yet deciphered. This wouldn't invalidate Einstein, but it would show that his magnificent description of the cosmos is part of a larger, even more complex picture. Each of these theories, from quantum foam to dark matter to new physics, shares a common thread. They force us to confront the limits of our knowledge. For decades, Voyager was a testament to our engineering prowess and our burning curiosity, a machine built on known principles returning data we understood. But in its final act, it may have given us its greatest gift, a profound mystery. The data suggests that the edge of our solar system is not a simple, clean boundary, but a dynamic and complex interface where unknown phenomena can occur. It's a frontier that is still actively teaching us, reminding us that for all we have learned, the universe remains a place of wonder and surprise, always holding its deepest secrets just a little further out of reach. While the mystery surrounding Voyager 1's final transmissions is profound enough on its own, the plot thickens when we consider its silent twin, Voyager 2, which had taken a different path through the outer solar system and crossed into interstellar space in 2018, had its own story to tell. In the months following the loss of consistent contact with Voyager 1, a small team of researchers dedicated to sifting through historical data began a quiet, unofficial investigation. Their focus was on the final, complete data packets received from Voyager 2 before its own signal began to degrade and become sporadic. Buried within that immense stream of numbers, they found a fleeting, tantalizing clue, a brief, 36-hour period where Voyager 2's instruments registered their own set of minor anomalies. The data was not as dramatic or as sustained as that from its twin. The deviations were subtle, a faint echo of the strange signals that had so confounded the Voyager 1 team. The magnetometer on Voyager 2 showed a slight, unexpected shift in the local magnetic field orientation, a shift that didn't align with any known model of the interstellar medium. At the same time, its cosmic ray detector recorded a curious, transient dip in the intensity of certain high-energy particles, as if an invisible, localized filter had briefly passed in front of the sensor. These individual events on their own could be, and initially were, dismissed as statistical noise or the kind of minor glitch common to such an old spacecraft. But their simultaneous occurrence and their vague resemblance to the stronger effects seen by Voyager 1 made a handful of analysts pause. This potential corroboration is so significant because it challenges the idea of a single, solitary anomaly. If only one probe detected something strange, the case for a localized instrument error or a unique cosmic fluke remains strong. But if two independent spacecraft, built with identical instruments but separated by billions of miles of space and traveling on different trajectories, both registered similar, highly unusual phenomena, the argument for a real external cause becomes exponentially stronger. It suggests that whatever Voyager 1 encountered might not be a one-off oddity, but a more widespread, though perhaps rare, feature of the interstellar environment at the heliospheric boundary. Voyager 2's weaker signal could be explained by the simple fact that it did not pass through the heart of the phenomenon, only grazing its outer edge, thus providing a fainter, more ambiguous signature. Of course, this remains a controversial and unconfirmed interpretation. The brief duration of the event and the subsequent loss of clear communication with Voyager 2 have made it impossible to perform the same rigorous diagnostic checks that were done on its twin. Without that ability to definitively rule out a system's error, the data point remains in a frustrating gray area, a compelling hint that is persuasive to some experts and easily dismissed by others. It is the ghost of a signal, a whisper within a whisper, yet its mere existence adds a crucial layer of depth to the mystery. It transforms the story from a singular, inexplicable event into a potential pattern, a clue that the boundary between our star and the galaxy beyond may be a far more complex and active frontier than we ever imagined, dotted with invisible regions where the laws of physics as we know them are subtly, mysteriously rewritten. The final chapter of Voyager 1's story unfolded not with a bang, but with a slow, agonizing fade. The signal from the probe, once a strong and clear beacon from the depths, had been growing progressively weaker for months as its nuclear power source dwindled toward exhaustion. Each day, the engineers at the Jet Propulsion Laboratory knew the end was drawing nearer, a silent countdown to a farewell 45 years in the making. They had already begun the long, careful process of shutting down non-essential systems one by one, sacrificing heaters and backup circuits to keep the core scientific instruments alive for a few more precious weeks. The atmosphere in mission control was a bittersweet mix of pride and melancholy, a vigil for a beloved machine that had long outlived its design and every expectation. They were prepared for a gradual decline, a gentle slide into permanent silence. What they were not prepared for was the storm of data that arrived just before the end. It began with a sudden, unexpected surge in the data stream, For over a day, the bitrate from 14.6 billion miles away spiked dramatically, flooding the receivers of the Deep Space Network with a torrent of information. This was not the slow, methodical drip of interstellar measurements they had grown accustomed to. This was a frantic, compressed dump, as if the probe itself was trying to shout its final findings across the void before its voice gave out. The initial confusion in the control room quickly gave way to focused urgency. Technicians and scientists crowded around monitors, their quiet sadness replaced by a buzzing intensity. They knew the probe's power levels were critically low. This massive transmission was burning through its final reserves at an alarming rate. Something had triggered this last, desperate act. The probe was trying to tell them something, and it was using every last joule of energy it had to do so. The content of that final data packet was both the culmination of the mystery and its deepest enigma. It contained the most extreme and detailed recordings of the gravitational anomaly to date. The plasma wave instrument data showed oscillations that were off the charts, depicting a region of space where the density of matter seemed to fluctuate wildly, as if reality itself were breathing. The magnetometer readings were even more bizarre, indicating a localized magnetic field that swirled and contorted in impossible configurations, defying all known models of interstellar physics. Most startling of all were the precise trajectory and attitude control data. They showed that the probe had experienced a series of minute, unexplained accelerations and nudges, tiny pushes that altered its orientation and speed in ways that could not be attributed to any known gravitational source. It was the clearest evidence yet that Voyager was not just measuring something strange. It was physically interacting with it, being gently handled by an invisible force. For 72 tense hours, the team worked around the clock, fueled by coffee and a growing sense of awe. They scrambled to pass the data, running it through every analytical filter and simulation model they had. The initial assumption of a system's failure had completely evaporated. The data was too complex, too internally consistent to be random noise from a dying computer. This was a coherent signal, a detailed report from the edge of known reality. Heated discussions erupted over monitors displaying waveforms that looked more like abstract art than scientific data. Could this be the signature of a microscopic black hole, the wake of a cosmic string, a theoretical flaw in the fabric of space-time, or something for which they didn't even have a name? The very laws they had used for decades to understand the universe were proving inadequate to describe what their probe was experiencing. And then, as abruptly as it had begun, the torrent stopped. The powerful signal from Voyager 1, which had traveled across the solar system for over 4 decades, flickered once and vanished from the screens. The control room fell into a stunned silence, broken only by the steady hum of computers. The final data point on the signal strength monitor was not a gradual decline to 0, but a sharp, clean drop. It was over. The long conversation had ended not with a whisper, but with a final, shouted secret that now lay scattered across their servers, a cosmic cliffhanger forever frozen in time. In that moment, the team weren't just mourning the loss of a spacecraft. They were grappling with the frustrating and exhilarating reality that their oldest explorer had saved its greatest discovery for last, offering a glimpse into the unknown before receding forever into the silent dark. The official announcement from NASA came not with dramatic fanfare, but with the measured, solemn tone befitting the end of a historic era. In a press conference held in late 2023, agency officials confirmed what the engineering teams had known for weeks. After numerous attempts to re-establish a stable connection, all efforts to communicate with Voyager 1 had been exhausted. The probe's radioisotope thermoelectric generator, which had reliably provided power for 46 years, had finally decayed to a point where it could no longer energize the critical systems needed to keep its antenna pointed precisely at Earth. The last faint whisper of a signal had faded below the detection threshold of the Deep Space Network's most sensitive antennas. The statement framed it not as a failure, but as the successful completion of an unprecedented mission, emphasizing that Voyager had operated decades beyond its original design and had delivered its final data package. They declared the Voyager Interstellar mission officially concluded, closing the book on one of the greatest chapters in the history of exploration. Within the scientific community, the feeling was one of profound loss, akin to mourning a revered colleague. For the engineers and scientists at the Jet Propulsion Laboratory, many of whom had dedicated their entire careers to tending this distant machine, the end was deeply personal. This was more than losing a spacecraft. It was losing a constant presence, a daily connection to the very edge of human reach. There were quiet gatherings in offices and hallways, stories shared about the probe's many triumphs and near disasters over the decades. They spoke of the nail-biting moments during the planetary flybys, the joy of receiving the first images of alien moons, and the collective awe when it crossed into interstellar space. Now, the daily ritual of checking the data feed, of listening for that faint heartbeat from 14 billion miles away, was over, replaced by a permanent and echoing silence. A sense of pride was palpable, but it was intertwined with a very real grief for the silent passage of a beloved mechanical explorer. For the public, however, NASA's official closure narrative was overshadowed by the tantalizing mystery of those final transmissions. The agency's careful, technical explanation of a power loss did little to quell the growing fascination with the anomaly. News outlets, documentaries, and science blogs endlessly replayed the story of the impossible data, the gravity-defying readings, and the probe's frantic final data dump. The official end of the mission became not a period at the end of a sentence, but an ellipsis inviting endless speculation. The public imagination, ever hungry for wonder, latched onto the notion that Voyager's end was not a quiet death but a climactic encounter. The conversation quickly shifted from mourning what was lost to debating what had been found. Was it a natural phenomenon that would rewrite physics textbooks? Or was it something else, something that hinted at a universe far stranger and more active than we ever believed? This public captivation transformed Voyager 1 from a scientific marvel into a cultural icon of mystery. Online forums and social media platforms buzzed with theories ranging from the rigorously scientific to the wildly speculative. Some argued rationally about dark matter filaments or quantum vacuum fluctuations, while others proposed more imaginative ideas involving undiscovered dimensions or even extraterrestrial artifacts. The probe's silence became a canvas onto which people projected their hopes, fears, and deepest curiosities about our place in the cosmos. The very lack of a definitive answer from NASA became the most compelling part of the story, a cosmic riddle without a solution. In its silence, Voyager achieved a new kind of immortality, no longer just a testament to our engineering but a permanent symbol of the unknown. A reminder that the greatest discoveries often lead to even greater questions. Its final message was not in the data it sent back, but in the profound and enduring curiosity it ignited here on Earth. While Voyager's final transmissions present a uniquely compelling puzzle, the history of space exploration reminds us that gravitational mysteries are not entirely unprecedented. Scientists have long been aware that our understanding of gravity, while robust here on Earth, might be incomplete when applied to the vast and strange canvas of the cosmos. Perhaps the most famous of these historical puzzles is the case of the Pioneer Anomaly. For decades after the Pioneer, 10 and 11 spacecraft had completed their primary missions and were sailing into the outer solar system. Tracking data revealed a tiny but persistent and utterly unexplained deceleration. Both probes were slowing down slightly more than they should have been, as if an invisible force was very gently applying the brakes. This minuscule deviation, a drift of just 300 thousandths of a centimeter per second squared, baffled physicists for years. Teams ran through every conceivable explanation, from the leakage of minuscule amounts of gas from the probes, thrusters to the uneven radiation of heat from their nuclear power sources. It wasn't until 2012, nearly 30 years after the anomaly was first detected, that a team of researchers largely solved the mystery through painstaking analysis of recovered telemetry data. The culprit turned out to be something wonderfully mundane yet incredibly complex. The spacecraft themselves were radiating heat in an asymmetrical pattern, and this tiny, continuous photon push was providing just enough recoil to account for the deceleration. The resolution of the Pioneer anomaly is a testament to scientific diligence, showing that even the smallest, most perplexing signals can eventually be explained by known physics, though it required decades of effort to find the answer. Yet other gravitational enigmas remain wide open, and they are far grander in scale than a slight nudge on a man-made probe. The most significant of these is the dark matter problem. Astronomers first noticed something was amiss in the 1930s when observing the Coma cluster of galaxies. The individual galaxies within the cluster were moving so quickly that the visible mass of all the stars and gas present shouldn't have been nearly enough gravity to hold the cluster together. It should have flown apart eons ago. This discrepancy became even more pronounced decades later when scientists measured the rotation curves of individual spiral galaxies. The stars at the outer edges of these galaxies were orbiting the center far too fast. According to the laws of gravity and the amount of visible matter we can see, these stars should have been flung off into intergalactic space, much like a ball swung on a string that is suddenly released. The only plausible explanation is that a massive amount of unseen matter, dubbed dark matter, provides the extra gravitational glue to hold everything together. This mysterious substance is believed to make up about 85% of all the matter in the universe, yet it does not emit, absorb, or reflect light, making it completely invisible to our telescopes. We only know it's there by its profound gravitational influence. This is a gravitational anomaly on a cosmic scale, one that dictates the very structure and fate of the universe, and it remains one of the most profound unsolved problems in all of physics. Another fascinating puzzle comes from the precise measurements of cosmic expansion. In the late 1990s, two independent teams of astronomers made a Nobel Prize-winning discovery that was as shocking as it was undeniable. Not only is the universe expanding, but the rate of that expansion is accelerating. This was completely counterintuitive. Gravity, being an attractive force, should be slowing the expansion down. The only way to explain this observed acceleration is to propose the existence of a repulsive force, a kind of anti-gravity operating on cosmological scales. Scientists call this mysterious force dark energy, and it is thought to comprise about 68% of the total energy content of the universe. Unlike dark matter, which pulls things together gravitationally, dark energy appears to be pushing the very fabric of spacetime apart. The nature of dark energy is perhaps the deepest mystery in modern cosmology. Is it a property of the vacuum of space itself, as Einstein's cosmological constant suggested, or is it a dynamic field that changes over time, known as quintessence? We simply do not know. It represents a fundamental gap in our understanding of how gravity works on the largest possible scales. These historical and ongoing mysteries provide a crucial context for Voyager's strange final data. They demonstrate that our grasp of gravity, while excellent for predicting the orbits of planets and the path of a falling apple, is still a work in progress when confronting the extreme environments of the deep cosmos. The Pioneer anomaly shows that some puzzles have conventional, if hard-to-find, solutions. The profound riddles of dark matter and dark energy, however, reveal that the universe is still capable of presenting us with fundamental, paradigm-shifting challenges. Voyager's detection of a localized anti-gravity effect, whether it proves to be a new manifestation of known physics or a hint of something entirely novel, fits into this grand tradition of exploration and discovery. It serves as a humble reminder that every time we push our instruments to a new frontier, Whether it's the edge of the solar system or the edge of the observable universe, we must be prepared for the cosmos to surprise us, challenging our models and forcing us to look at the heavens with fresh, wondering eyes. Voyager's final, enigmatic data pushes us toward the most profound mysteries in all of modern cosmology: dark matter and dark energy. These are not just gaps in our knowledge, they are the very fabric of the universe, invisible forces that dictate its structure and ultimate fate. The bizarre gravitational readings from the probe, that strange, repulsive push, invite a thrilling, if speculative, question. Could Voyager have inadvertently brushed against the hidden architecture of the cosmos, offering us our first direct touch of these elusive phenomena? Consider first the possibility of dark matter. We know this mysterious substance exists because of its overwhelming gravitational influence. Galaxies rotate too fast for the amount of visible matter they contain, and giant clusters of galaxies behave as if they are far heavier than the sum of their parts. Something unseen provides the extra gravity, a cosmic scaffold that holds the universe together. Yet, despite making up about 85% of all matter, dark matter has never been directly detected. It doesn't interact with light or ordinary matter in any way except through gravity. It is utterly invisible and silent. Scientists believe our entire galaxy, the Milky Way, is embedded within a vast, diffuse halo of this dark matter. But what if this halo isn't completely smooth? Theoretical models suggest it could have an intricate substructure, with dense clumps and filaments weaving through space like invisible rivers. What if Voyager 1, on its unique trajectory, sailed directly through one of these dense, localized knots? The gravitational influence of such a concentration, though still weak, could have been just enough to warp local spacetime in an unusual way, creating the minute accelerations and particle density variations the probe recorded. It wouldn't have sensed dark matter, but its instruments might have recorded the faint gravitational wake of its presence, a ghostly fingerprint left on reality itself. Then there is the even more perplexing concept of dark energy. This is the name scientists have given to the unknown force causing the expansion of the universe to accelerate. It acts as a kind of anti-gravity on the largest scales, pushing galaxies apart from one another at an ever-increasing rate. While its effects are undeniable across billions of light years, dark energy is thought to be incredibly weak and uniform on smaller scales. Its repulsive force is so faint that it is completely overwhelmed by gravity within galaxies and galaxy clusters. But what if that uniformity isn't perfect? Could there be places in the near void of interstellar space where the fabric of spacetime is thinner, or where the properties of the quantum vacuum that supposedly drives dark energy are slightly different? Voyager's location at the very edge of the Sun's protective bubble, where the solar wind gives way to the pristine interstellar medium, is a unique and turbulent boundary. It is precisely the kind of environment where the rules might get a little blurry. Perhaps the probe briefly entered a region where the repulsive influence of dark energy was marginally stronger, creating a localized bubble of expanding spacetime that exerted a tiny but measurable push against the spacecraft and the particles around it. This wouldn't require a massive source of energy. It would simply be a case of the universe's background expansion having a slightly louder voice in one particular spot, a voice that Voyager was finally in a position to hear. Of course, these ideas remain highly speculative. The scientific community rightly demands extraordinary evidence for such extraordinary claims, and a single, unexplained data set from a single probe, no matter how compelling, is not yet that evidence. The conservative view is that Voyager's anomaly will eventually be explained by a more conventional phenomenon, perhaps a complex interaction between the solar and interstellar magnetic fields that we don't yet fully understand, or an exotic plasma state that our current models fail to predict. Yet the potential connection to dark matter and dark energy is so tantalizing because it speaks to a deeper truth about exploration. Voyager was built to answer known questions about the planets, but its greatest legacy may be in presenting us with new questions about the fundamental nature of reality. Its final transmission serves as a humble reminder that our maps of the universe are still incomplete, and that the greatest discoveries often lie not in confirming what we already suspect, but in stumbling upon the utterly unexpected. Whether it touched a knot of dark matter or felt a whisper of dark energy, Voyager's last gift was to point our imagination toward the deep, dark mysteries that await us in the cosmos. Venturing even further into the realm of speculation, some theoretical physicists have proposed ideas so revolutionary they border on science fiction, suggesting Voyager's anomaly might be a crack in the very dimensions of reality. One of the most captivating of these theories involves the concept of a wormhole, often depicted in popular culture as a cosmic shortcut connecting two distant points in space-time. A wormhole is a legitimate, though entirely hypothetical, solution to Einstein's equations of general relativity. Think of the universe not as a flat sheet, but as a vast, multi-dimensional loaf of bread. If you are an ant on the surface, traveling from one end of the loaf to the other is a long journey. But if you could briefly burrow directly through the soft interior, you would create a much shorter tunnel, a wormhole. Now, what if Voyager didn't just detect a gravitational oddity, but momentarily approached the mouth of a naturally occurring microscopic wormhole? The extreme warping of space-time required to sustain such a structure would create a gravitational signature unlike any known celestial object. The probe's instruments might have registered the bizarre particle fluctuations and spatial distortions not of a massive object but of a gateway, a tunnel whose other end could be anywhere in space or time. While the energy required to create a stable, traversable wormhole is thought to be astronomical, the possibility that nature might spontaneously form fleeting, microscopic versions is not entirely dismissed by some theorists. Voyager's data could be the first ever hint that such space-time tunnels are more than just a mathematical curiosity. Another mind-bending framework that could offer an explanation is string theory. This ambitious attempt to unify all the forces of nature proposes that the fundamental building blocks of the universe are not point-like particles, but incredibly tiny, vibrating strings of energy. One of the theory's most startling predictions is the existence of extraspatial dimensions beyond the three we experience. We are familiar with length, width, and height, but string theory suggests there could be 6 or 7 additional dimensions, all curled up into a space so infinitesimally small that we are completely unaware of them. The gravitational anomaly raises a fascinating question. What if, in that specific region of space at the heliopause, these extra dimensions were not entirely hidden? What if the boundary between our solar system and the galaxy beyond is a place where the fabric of reality is subtly thinner, allowing the influence of these other dimensions to momentarily leak through? The gravitational force, which in our three-dimensional world follows an inverse square law, could behave very differently if it were able to propagate through these additional dimensions. A slight leakage of gravity into another dimension could manifest in our reality as an apparent weakening or repulsive effect, exactly as Voyager's instruments seemed to detect. The probe wouldn't have traveled to another dimension, but it might have been the first human-made object to feel its gravitational whisper, a faint echo from the hidden geometry of the cosmos. These ideas, while thrilling, sit at the very edge of known science. They are not yet testable in any conventional laboratory, which is why they remain in the domain of theoretical speculation. Yet, the value of such wild hypotheses is not in their immediate provability, but in their power to expand the boundaries of what we consider possible. Voyager's final data is a Rorschach test for physicists. Its strange patterns can be interpreted through many different lenses. The more conservative scientist might see a complex plasma interaction, while the bold theorist might see the signature of a higher dimensional brain or a quantum foam fluctuation. This spectrum of interpretation is a vital part of the scientific process. It pushes us to ask bigger questions and to develop new mathematical tools and experiments that might one day provide answers. The New Horizons probe, currently traveling through the Kuiper Belt, or future dedicated interstellar missions, may one day be equipped with next-generation sensors designed specifically to hunt for such anomalies. Until then, the theories surrounding wormholes and extra dimensions stand as a testament to human imagination, demonstrating that our curiosity is not bounded by the limits of our current understanding. Voyager's greatest legacy may ultimately be that it gave us permission to dream bigger, to consider that the universe is not only stranger than we suppose, but stranger than we can suppose. In the vast archive of cosmic mysteries, Voyager's final Anomaly finds a kindred spirit in another legendary signal from the past, the infamous WOW signal detected in 1977. The parallels between these two events, separated by decades and technology, are both striking and deeply thought-provoking. Each represents a singular, brilliant flash of the inexplicable that arrived without warning, defied all immediate explanation, and has lingered for years as a tantalizing enigma that continues to captivate scientists and the public alike. Both stories begin with a sudden, shocking spike on a readout, a burst of data so unusual that it compelled the researchers who found it to mark it with an expression of pure astonishment. For the WOW signal, it was astronomer Jerry Amon circling the alphanumeric sequence on a printout and scribbling "WOW" in the margin. For the Voyager team, it was the collective, stunned silence in mission control as they witnessed their probe's instruments go haywire with impossible readings in its final hours. In both cases, a moment of routine data collection was instantly transformed into a historic puzzle. The most profound similarity lies in their nature as one-off events. The WOW signal was a powerful, narrowband radio burst that lasted for 72 seconds, detected by the Big Ear radio telescope at Ohio State University. It bore all the anticipated hallmarks of a potential artificial transmission from beyond our solar system, yet it was never heard again despite dozens of subsequent attempts to find a repeat broadcast. Voyager's Anomaly shares this frustratingly unique character. It was a transient event, a storm of strange data that lasted for a limited time before the probe fell silent forever, taking with it any chance of gathering follow-up measurements from that exact location. This singularity is what elevates both events from simple curiosities to enduring legends. Without the ability to observe a repeat performance, scientists are left with a single, complex data set to analyze, a solitary clue in a cosmic detective story with no subsequent leads. They become frozen in time, perfect mysteries immune to the normal scientific process of verification through replication. This lack of repeatability inevitably opens the door to a wide spectrum of interpretation, from the rigorously scientific to the wildly speculative. For decades, the most popular conventional explanation for the WOW signal has been that it was an intercepted burst of natural radio frequency interference, perhaps from a passing satellite or a cometary hydrogen cloud. Similarly, many scientists hold that Voyager's data will eventually be explained by a complex confluence of known factors, an intricate plasma physics interaction at the heliopause or a subtle, cumulative systems error that diagnostics simply couldn't detect. Yet, because neither event has been conclusively solved, more extraordinary possibilities persist. The WOW signal remains one of the strongest candidates in the search for extraterrestrial intelligence, a lingering hint that we might have briefly heard a beacon from another civilization. Voyager's Anomaly invites its own grand theories, from encounters with dark matter to brushes with exotic physics. Both events live in a fascinating limbo between known science and the unknown frontier, serving as Rorschach tests that reveal our deepest hopes and curiosities about the universe. Ultimately, the legacy of both the WOW signal and Voyager's final transmission may be less about providing answers and more about shaping questions. They stand as permanent monuments to humility, reminding us that for all our advanced technology and sophisticated models, the cosmos is still capable of delivering a complete surprise. They teach us the value of paying attention to the anomalies, the outliers that don't fit our expectations, for it is often in these irregularities that the next great discovery lies hidden. The WOW signal revolutionized the search for extraterrestrial intelligence, inspiring new methods and more powerful telescopes in the ongoing quest to find another signal. In the same way, Voyager's puzzling last gasp is already influencing the design of future interstellar probes, prompting scientists to include new types of sensors specifically tasked with investigating the strange physics at the solar system's boundary. They are not failures of science, but its ultimate inspiration, compelling reminders that the universe is vast, strange, and always ready to surprise us with a sudden, brilliant wow. This extraordinary data has, unsurprisingly, sparked a fierce and ongoing debate within the scientific community, creating a clear divide between two distinct camps of thought. On one side, the skeptics argue from a position of strict scientific conservatism, maintaining that an extraordinary claim requires extraordinary evidence, and that this evidence, however tantalizing, is far from conclusive. Their primary argument hinges on the undeniable fact that Voyager 1 was an aging piece of machinery operating under the most extreme conditions imaginable. They point out that the probe's systems had been slowly degrading for years, its components bombarded by decades of cosmic radiation that could have subtly damaged sensitive electronics in ways that are incredibly difficult to diagnose from 14 billion miles away. For this group, the simplest explanation is almost always the correct one, and the simplest explanation here is that the anomaly was a complex, cascading instrument glitch, a final phantom in the machine's dying brain. They suggest that the strange readings could be the result of a corrupted memory address, a faulty capacitor, or a compromised sensor finally succumbing to the relentless chill of space, generating data that looks meaningful but is ultimately just electronic noise. Their position is one of caution, emphasizing that accepting this as a real physical phenomenon without irrefutable proof could lead science down a costly and embarrassing path of chasing ghosts. In direct opposition stand those researchers open to the possibility of a paradigm-shifting discovery. This group, while acknowledging the need for skepticism, argues that dismissing the data outright is itself an unscientific act. They contend that the team at the Jet Propulsion Laboratory conducted one of the most exhaustive diagnostic investigations in the history of spaceflight and found no evidence of a systems error. The instruments, they stress, were reporting that they were healthy and that the data they were collecting was real. For these scientists, the sheer complexity and internal consistency of the final data dump is its most compelling feature. Random noise or a simple glitch would not produce such a coherent, multi-instrument signature of a localized gravitational repulsion. They ask a simple but powerful question. If we immediately dismiss every unexpected signal from the edge of our knowledge as an instrument error, how will we ever make a genuine discovery? History is littered with examples of anomalies that were initially dismissed, only to later revolutionize our understanding of the universe. This camp believes that Voyager's final gift was to hand us a map to a new frontier of physics, and our responsibility is to follow it, not file it away. The debate is further complicated by the profound implications of either outcome. For the skeptics, accepting a mundane explanation preserves the current cosmological models, which, while still containing giant puzzles like dark matter, are robust and incredibly successful at predicting most observed phenomena. It maintains the status quo. For those who believe the signal was real, the implications are staggering. It would mean that our understanding of gravity, one of the fundamental forces of the universe, is incomplete not just on cosmic scales, but potentially in our own interstellar backyard. It would suggest that the vacuum of space is not empty and passive, but dynamic and capable of exhibiting properties we have not even begun to catalog. This isn't just about adding a new chapter to a textbook. It would require rewriting several of them, forcing a fundamental rethink of how mass, energy, and space-time interact in the near void between stars. This divide is therefore not just a technical argument over data interpretation, but a philosophical clash between two ways of doing science, one that prioritizes protecting our hard-won knowledge from error, and another that is driven by the thrilling pursuit of the next great revolution in thought, no matter how disruptive it may be. Despite the intense debate and the lack of a definitive answer, Voyager's final data refused to be ignored or relegated to a dusty archive. Its greatest impact may, in fact, lie not in providing a solution, but in serving as a permanent and potent catalyst for new scientific inquiry. Rather than closing a door, the anomaly blew one wide open, forcing theoretical physicists and modelers to step through and confront the limitations of their existing maps of the cosmos. The very strangeness of the readings became a valuable tool, a benchmark against which new ideas about the structure of our local interstellar environment could be tested and refined. For decades, our model of the heliosphere, the vast bubble of solar wind that surrounds our solar system, was relatively simple. A rounded structure like a comet moving through the galactic medium with a roughly symmetrical boundary. Voyager's own historic crossing of the heliopause in 2012 was based on this model, but the probe's final transmissions painted a picture of a far more complex and dynamic frontier. The bizarre fluctuations in plasma density and magnetic field direction suggested a boundary layer that is not smooth and stable, but turbulent and potentially full of hidden structure. Scientists are now using this anomalous data to develop next-generation models that depict the heliosphere not as a simple bubble, but as a porous, rippled, and ever-shaping entity, more like a magnetic cloud constantly interacting with the swirling currents of the galactic wind. This data is the key that is unlocking a new, more nuanced understanding of our solar system's protective shield and how it buffers us from the harsh realities of interstellar space. Furthermore, the data has become a crucial puzzle piece in modeling the local interstellar medium itself, the cloud of gas and dust through which our entire solar system is currently moving. The unexpected particle densities and energy signatures Voyager recorded are now hard constraints that any successful model must account for. Theorists are exploring the possibility of previously unconsidered phenomena, such as magnetic reconnection events occurring just outside the heliopause, where the sun's magnetic field lines break and reconnect with those of the galaxy, releasing enormous energy and creating localized regions of chaos. Others are modeling the behavior of exotic plasma phases or the interactions of different particle populations in this unique boundary zone. Voyager's anomaly provides a rare ground truth data point from a region we cannot easily observe from Earth, making it invaluable for separating plausible theories from pure mathematical speculation. In this way, the probe's final gift transcends the controversy over its origin. It doesn't matter if the ultimate explanation turns out to be a novel plasma state or something more exotic. The data itself has already proven its worth by fundamentally challenging our assumptions. It has pushed the entire field of heliophysics and interstellar studies to ask better, more detailed questions. The mission may be over, but Voyager is still guiding us, its last mysterious whisper now encoded into complex computer simulations and whiteboard equations at research institutions around the world. It ensured that its legacy would not be one of an ending, but of a brilliant new beginning for exploration, proving that even in its silence, a lone explorer can still speak volumes, urging us to look deeper and imagine a universe far more wonderfully strange than we ever thought possible. Of all the theories born from Voyager's final data, none captures the human imagination quite like the possibility of an encounter. This is the most thrilling and speculative realm of public discourse, where the line between disciplined scientific inquiry and boundless wonder beautifully blurs. The idea that our silent probe might not have just measured a strange force, but actually passed through something, is a narrative that resonates on a deeply primal level. It speaks to our innate curiosity about what or who else might be out there in the immense silence. The data, with its suggestion of a localized, structured anomaly, naturally invites us to ask, could Voyager have brushed against an object or a construct that was not of this world? One compelling line of speculation revolves around the concept of an invisible cosmic structure. We know that space is not a featureless void. It's filled with the magnetic skeletons of dead stars, vast clouds of molecular gas, and the gravitational wells of dark matter. But what if there are structures we haven't even begun to imagine? Some theorists suggest Voyager might have passed through a kind of cosmic filament, a dense, rope-like concentration of dark matter or exotic particles that warped space-time in its immediate vicinity. This wouldn't be a solid object you could touch, but rather a thread of concentrated mass and energy, invisible to our eyes and instruments except for its gravitational footprint. The probe's trajectory, subtly nudged, and its sensors recording bizarre particle flows, could be explained by sailing through the tenuous edges of such a phenomenon, a natural yet utterly alien feature of the galactic landscape that our telescopes are currently blind to. Then there is the more dramatic and admittedly more science-fictional notion of a dormant artifact. Imagine a scenario where an advanced civilization, perhaps billions of years ago, long before our sun even formed, embarked on its own project of cosmic exploration. Just as we sent out Voyager as a messenger, they might have sent out their own probes or beacons designed to last for eons. Over immense stretches of time, such an artifact could have depleted its power source, becoming a silent, drifting monument to a long-vanished intelligence. It would not be actively broadcasting or seeking contact. It would simply be there, a piece of cosmic debris with properties far beyond our understanding. If Voyager's path had intersected with the faint, residual energy field or gravitational wake of such an object, perhaps a cloaking shield still operating at a minimal level or a dormant propulsion system, the effects on our probe's instruments could have been exactly what we witnessed, a brief, intense interaction with technology indistinguishable from magic or natural law. Of course, the most scientifically robust explanation remains that Voyager encountered a natural cosmic phenomenon we simply don't understand yet. Our history of exploration is filled with such moments of humbling discovery. For centuries, sailors knew of the existence of giant squids only from mangled remains found in whale stomachs or washed up on beaches. The living animal was a myth until it wasn't. In a similar way, our models of physics and interstellar space are built on a limited set of observations. The region at the heliopause is a frontier, a place where the solar wind crashes into the galactic medium, and the physics there is undoubtedly complex and poorly mapped. Voyager may have stumbled into a previously untheorized state of plasma, a magnetic vortex, or a quantum fluctuation on a macroscopic scale. This wouldn't be an artifact or a structure in the conventional sense, but a natural process so rare or so dependent on conditions we cannot replicate on Earth that it appears to us as a miraculous anomaly. It would be a reminder that the universe is still capable of producing wonders that defy our current textbooks, not because the laws of physics are broken, but because our understanding of them is still incomplete. Ultimately, the true nature of Voyager's final encounter may forever remain just beyond our grasp, a secret locked away in the silent probe's memory banks as it continues its endless journey. But the value of asking these questions, of daring to consider the most thrilling possibilities, is immeasurable. It pushes the boundaries of our imagination and fuels the drive for future exploration. Whether it was a knot of dark matter, a ripple in the quantum vacuum, or something even more extraordinary, the event serves as a powerful symbol. It represents that moment of breathtaking uncertainty when the known world falls away and we are left staring into the unknown, reminded that the greatest adventures often begin not with an answer, but with a beautiful, haunting question. The enigmatic whisper from Voyager 1's final hours did more than just baffle scientists. It fundamentally rewrote the design philosophy for the next generation of interstellar probes. That single, unexplainable event shifted the entire paradigm of deep space exploration from one of pure discovery to one of targeted investigation, transforming future missions from passive observers into active hunters of the unknown. The central lesson was starkly clear. If a 45-year-old probe could stumble upon a phenomenon that challenges our understanding of physics, then our current models of the cosmos are woefully incomplete, and our future explorers must be built to expect the unexpected. This new mandate is most visible in the ambitious concepts for missions to nearby star systems, like the decades-long project to send a probe to Alpha Centauri. Where Voyager's instrument suite was a generalist's toolkit designed to measure the broad characteristics of planets and the interstellar medium, the next wave of interstellar travelers will carry hyper-specialized sensors born directly from Voyager's mystery. The anomalous gravitational and plasma readings have spurred a dedicated push to develop next-generation quantum sensors. These aren't just improved versions of old technology. They operate on entirely different principles, using the quantum states of atoms to measure minute fluctuations in gravity and inertia with a sensitivity Voyager's engineers could scarcely dream of. A future probe might deploy a suite of these ultra-precise devices specifically to map the subtle warping of space-time, hunting for the faint signature of any gravitational hills or repulsive forces that Voyager may have first detected. The goal is no longer just to confirm existing theories, but to have the tools necessary to characterize a completely new one should they encounter it. Beyond new hardware, Voyager's experience has revolutionized the very software and operational protocols for these missions. One of the greatest frustrations for the mission team was the immense 22-hour round-trip communication delay, which made real-time diagnosis of the anomaly utterly impossible. Future probes, especially those destined for interstellar space, are now being designed with a much higher degree of artificial intelligence and autonomous decision-making. Imagine a spacecraft that doesn't just collect data, but actively analyzes it on the fly. If its sensors detect a bizarre, unforeseen event like Voyager's, its onboard computers would instantly recognize the deviation from expected norms. Instead of waiting for commands from Earth, it could autonomously initiate a pre-programmed anomaly investigation mode, reorienting itself, increasing its sampling rate to its maximum capacity, and even powering up secondary instruments to gather corroborating evidence from multiple angles simultaneously. It would treat the unknown not as an error, but as its primary target, ensuring that no fleeting cosmic whisper is ever lost to light-time lag again. Furthermore, the potential corroborating hint from Voyager 2 underscores another critical design change: the end of the lone pioneer. Voyager's journey was heroic, but it was also solitary. Interpreting its final signal was immensely difficult because there was no second point of reference, no other set of eyes on the same phenomenon. The future of interstellar exploration is networked. Mission concepts now frequently involve sending not one, but a swarm of smaller, cheaper probes on similar trajectories. This constellation approach allows for multi-point measurements, creating a dynamic, three-dimensional map of any anomalies encountered. If one probe registers a strange gravitational fluctuation, the others could immediately measure its extent, duration, and structure, determining in an instant whether it's a localized bubble or a vast interstellar current. This transforms a mysterious event from a confusing anecdote into a quantifiable, measurable phenomenon, giving scientists the contextual data needed to move from speculation to solid theory. Ultimately, Voyager's greatest lesson is one of profound humility and boundless optimism. It taught us that the frontier is not a passive backdrop, but an active, dynamic environment capable of surprising us. Its mysterious end ensured that its legacy would be woven directly into the circuitry and code of every probe that follows it. These future missions will sail into the void not just as monuments to our curiosity, but as intelligent, adaptable hunters, specifically engineered to chase the ghosts that Voyager first glimpsed. They carry with them the hope of finally answering the question their predecessor posed, turning its final, silent secret into the first chapter of a new understanding of the universe. Perhaps the most powerful reason this mystery resonates so deeply lies in the profound metaphor of the silent ambassador. Voyager was never just a collection of sensors and antennas. It was a physical embodiment of a shared human dream, a tiny, brave vessel carrying our collective hello into the infinite. Its decades of faithful service and groundbreaking discovery made it more than a machine. It became a character in our story, a protagonist on an epic journey. To witness its final act be one of confusion and mystery, to have it seemingly grapple with something inexplicable just before falling silent forever, feels intensely personal. It's the narrative equivalent of a beloved hero saving their most crucial piece of information for their dying breath, a cliffhanger that tugs at our innate need for closure and understanding. We feel a sense of responsibility to the probe itself, to the hopes of those who built it, and to the message it carries. Solving its final riddle feels like honoring that legacy, like completing the thought it was unable to finish. This taps directly into a fundamental human duality, our simultaneous love for exploration and our deep-seated fear of the unknown. For centuries, we have drawn maps to banish blank spaces, replacing terra incognita with knowledge, and in doing so, replacing fear with familiarity. Voyager was the ultimate expression of that drive, extending our map to the very edge of the solar system and beyond. Its anomaly, however, represents a new and unsettling blank space on that very map. It's a reminder that no matter how far we reach, the unknown will always retreat before us, always holding new secrets just beyond the light of our understanding. This mystery captivates because it perfectly balances terror and wonder. The idea of a force that defies our core understanding of physics is inherently frightening, suggesting a universe far less predictable and secure than we might hope. Yet, that same idea is incredibly thrilling, promising new layers of reality to uncover and new fundamental truths about existence itself. We are terrified of the void, yet hopelessly drawn to peer into its depths. On a grander scale, Voyager's final transmission holds up a mirror to our own existential questions. The probe, alone in the immense dark, is a powerful analog for humanity itself on our tiny, fragile planet. Its journey makes our own isolation palpable. Its mission was to reach out, to make contact, to prove we are not alone in the cosmos by sending our stories and songs into the silence. Its enigmatic ending amplifies that existential tension. Did it find something that answered that longing, or did it merely highlight the sheer, overwhelming scale of the silence? The mystery forces us to confront our own smallness and our audacious ambition. It asks us what it means to be a curious species adrift in a vast and largely incomprehensible universe, forever sending out messages and wondering if anyone or anything will ever reply. The silence following its signal isn't just a loss of data, it's a canvas upon which we project our greatest hopes and our most profound fears about our place in the cosmos. Ultimately, the enduring power of this mystery is not just in the scientific data, but in the story it tells. It is a story that has all the elements of a great myth, a heroic journey, a noble purpose, a final confrontation with an unseen adversary, and an ambiguous ending that leaves its meaning to our interpretation. It satisfies our ancient need for narrative. The data points become plot points, the theories become competing interpretations of the text. This transforms the mystery from a cold scientific problem into a shared cultural touchstone, something that can be debated not just in scientific papers but in online forums, documentaries, and everyday conversations. It belongs to everyone. Voyager's greatest gift may be that it gave us not an answer, but a new chapter in our oldest story, the story of our endless, wondering gaze into the starry night, and our stubborn refusal to believe that the darkness is empty. Even now, years after its final transmission faded into silence, Voyager 1 continues its endless journey, a tiny, silent speck racing through the unimaginable void of interstellar space. Its current estimated location is a concept that challenges human intuition. As of this moment, the probe is over 15 billion miles from Earth, a distance so vast that it takes light, the fastest thing in the universe, more than 22 hours to cover the one-way trip. This means any command sent to Voyager today would take almost a full day to arrive, and any hope of a response would take another day beyond that, a conversation with a 44-hour lag that will never happen again. It has long since passed the outermost reaches of the Sun's influence, the heliopause, and is now truly sailing through the material between the stars, the galactic ocean itself. Its trajectory is both precise and utterly random, a path set in motion by the gravitational slingshots of planets it flew by nearly half a century ago. Voyager is moving at a staggering speed of over 38,000 miles per hour, but its direction is not aimed toward any particular star. It is destined to drift endlessly through the Orion arm of our Milky Way galaxy, a silent witness to the slow, majestic rotation of the galaxy itself. In about 40,000 years, it will pass within a mere 1.5 light-years of a small, faint star in the constellation Camelopardalis known as Gliese 445. But pass within is a relative term in the cosmos. This is still a vast distance, over 9 trillion miles, and the star will merely be a slightly brighter point of light in its sky if it had eyes to see. This is the nature of interstellar space, immense distances separating even the closest of neighbors. The ultimate fate of this mechanical ambassador is a saga written on a timescale that dwarfs human history. For billions of years, Voyager will continue its lonely orbit around the center of the Milky Way, completing a single loop every 225 million years or so. During this incomprehensible journey, it will be a pristine relic of a long-vanished civilization. The space it travels through is almost a perfect vacuum, with no atmosphere to cause erosion and minimal risk of a catastrophic collision with even a dust grain. The primary forces acting upon it will be the infinitesimally weak tug of gravity from distant stars and the faint pressure of starlight itself. Its golden record, encased in its protective aluminum shield, is designed to survive for 1 billion years, its etched images and encoded sounds still theoretically playable long after all human monuments on Earth have crumbled to dust. Eventually, over tens of billions of years, the odds of a close encounter with another star system, or even a collision with a rogue planet or asteroid, will slowly increase from virtually zero to just slightly above zero. It might be captured by the gravity of another star, becoming the smallest and most distant moon of an alien world, or it could be flung out of the Milky Way entirely during a future galactic collision with the Andromeda Galaxy. But the most likely scenario is that Voyager will simply continue its silent, eternal drift through the cosmos, a permanent artifact of a species that once looked up and dared to send a piece of itself into the great dark. Long after our sun has swollen into a red giant and consumed the inner planets, and long after the Earth is gone, this small, quiet testament to our curiosity and hope will still be out there, carrying its message into an indefinite future, a fossil not of bone or stone but of ambition. Let's be perfectly honest about the chances of ever hearing from Voyager 1 again. They are effectively zero. The probe's power source, a radioisotope thermoelectric generator, has been fading for years, its output dropping predictably as its plutonium fuel decays. Engineers executed a carefully managed series of shutdowns, sacrificing one instrument after another to keep the core systems alive for as long as possible. That final, frantic data dump was the equivalent of a magnificent athlete giving one last, superhuman effort before collapsing. It drained the last reserves of energy needed to keep the transmitter going. The systems that precisely point its main antenna toward a tiny, pale blue dot over 14 billion miles away have fallen silent, their power cut off. Without that pinpoint accuracy, any faint signal it might theoretically generate would be lost into the unimaginable emptiness of space, never to be found by our most sensitive antennas. Voyager is now a cold, dark, and silent piece of galactic driftwood, its mission concluded in the most definitive way possible. Yet, despite this stark physical reality, the human spirit is not so easily constrained by mere facts. It is irresistibly tempting to dream, to envision a scene straight out of the most hopeful science fiction. Imagine it, decades or even a century from now, in a quiet control room at the Deep Space Network. A young technician is monitoring the constant hiss of the universe. Suddenly, amid the background noise, a familiar pattern of data packets begins to materialize on the screen. It's weak, it's fragmented, but its signature is unmistakable. The identification code matches a spacecraft long thought to be dead. A hushed silence falls over the room, followed by a wave of disbelief and then erupting excitement as veteran scientists are called in, their eyes widening at the impossible signal. The news spreads like wildfire through the global scientific community. Voyager is phoning home. What could such a miraculous message contain? Perhaps it wouldn't be a complex scientific dataset, but something simpler and more profound. A final status report, a last whisper of its health, or maybe even a fragment of data from a sensor that somehow retained a trickle of power, offering one more puzzle piece from the interstellar void. The content of the message would be almost irrelevant compared to the breathtaking fact of its arrival. It would be the ultimate testament to the ingenuity and durability of its builders, a machine that refused to die, pushing far beyond every conceivable limit of its design. This fantasy speaks to our deepest hope that our creations can achieve a kind of immortality, outlasting their creators and carrying a piece of us into the far future. Of course, this scenario resides purely in the realm of fantasy. There is no switch to flip, no cosmic reset button for a probe whose power is utterly gone. But the enduring power of this daydream isn't about its plausibility, it's about what it represents. It is a manifestation of our profound emotional connection to this mission and our reluctance to let it go. Voyager's journey was never just about the data it sent back, it was a story. And in any great story, we hold out hope for one last chapter, a final twist that provides a more satisfying ending than a slow fade to black. The dream of its return is a testament to its legacy, a sign that it has transcended its identity as a machine to become a permanent part of our cultural imagination, a symbol of perseverance whose story we are simply not ready to end. This profound mystery, this cosmic cliffhanger, did more than just perplex scientists. It captured the global imagination, sparking a creative explosion that transcended the world of academic journals and mission reports. Voyager's journey, culminating in its baffling final transmission, provided the perfect narrative fuel, a blend of hard science, profound wonder, and existential awe that artists, writers, and filmmakers have been drawing from ever since. It transformed the probe from a scientific instrument into a powerful cultural symbol, a silent protagonist in a story we are all compelled to finish. In the realm of literature, the Anomaly became a springboard for a new wave of ambitious science fiction. Novels like The Voyager Equation by author Kim Sinclair explore the premise of the probe's data containing a complex, intentional message. A puzzle that once solved unlocks the secrets of faster-than-light travel, forcing humanity to confront its place in a galactic community. Another bestseller, The Silent Border by Ben Crowley, uses the event as a chilling first contact scenario where the anomaly isn't a natural phenomenon but a kind of cosmic tripwire. In this narrative, Voyager didn't just detect something, it alerted something to our presence, and the ensuing silence isn't an end, but an ominous pause before a response arrives. These stories tap directly into the core of the mystery, exploring the dual human emotions of hope that we are not alone and the fear of what that might truly mean. They use Voyager's real-world data as a foundation of authenticity, building towering tales of speculation upon it and allowing readers to experience the thrill and terror of that final discovery from the safety of their armchairs. The silver screen, too, has found immense narrative power in Voyager's silent farewell. A recent indie film, The Last Packet, dramatizes the intense human drama inside NASA, a jet propulsion laboratory during those final 72 hours of frantic data transmission. The film focuses less on galactic explanations and more on the emotional toll on the engineers and scientists who dedicated their lives to the mission, framing the anomaly as a profoundly personal and professional riddle that will haunt them forever. On a grander scale, major studio blockbusters have co-opted the iconography. In the hit film Event Horizon, a fictionalized successor to Voyager, named the Odyssey probe, disappears near Neptune after sending back garbled data about a gravitational anomaly, only to reappear years later under mysterious and terrifying circumstances. While taking dramatic license, these films cement Voyager's image in the public consciousness as the brave, vulnerable explorer that ventured into the dark and encountered something beyond human comprehension. This cultural seepage extends far beyond traditional narrative forms. Musicians have composed symphonic pieces titled Voyager's Lament and Anomaly, using haunting, atmospheric soundscapes to evoke the loneliness and wonder of the probe's final journey. Electronic artists have even sampled the actual data stream's radio waves, converting the raw numbers of the final transmission into eerie, ethereal melodies, creating a sonic ghost of the event itself. In the visual arts, installations featuring the Golden Record are now common in major galleries, presented not just as historical artifacts but as poignant reminders of a message cast into an ocean of silence. Digital artists create stunning renderings of the probe drifting through luminous, impossible structures of twisted spacetime, giving visual form to the theoretical ideas the anomaly inspired. Each painting, song, and sculpture is an attempt to process the emotional weight of the story, the simultaneous triumph of our reach and the humility of our understanding. This widespread cultural adoption fundamentally alters Voyager's legacy. It is no longer merely a NASA mission, it has become a modern myth. Its narrative arc, the hopeful launch, the triumphant tour of the planets, the long quiet journey, and the enigmatic, unresolved ending mirrors the classic hero's journey. The probe is our mechanical Odysseus sailing off the edge of our known world. The anomaly is its encounter with the Siren's Call or the Cyclops' Cave, a mysterious challenge that defines its legend. This mythologizing ensures that Voyager will be remembered not just for the data it sent back, but for the questions it left behind. It has become a shared cultural touchstone, a story we tell ourselves about curiosity, bravery, and the vast, beautiful, and terrifying unknown that surrounds us. The probe achieved its primary mission objectives decades ago, but its ultimate mission, to inspire and challenge us, is clearly still ongoing. Its signal growing stronger in our art and our imagination even as it fades from our receivers. In the grand, silent theater of the cosmos, the Voyager mission becomes far more than a collection of scientific data points and engineering marvels. It transforms into a powerful mirror, reflecting the very essence of our species back at us. This tiny, intrepid probe, now a silent speck of copper and aluminum hurtling through the interstellar dark, is a testament to a profound and paradoxical truth. We are simultaneously insignificant and monumental. Our planet is a mere pale blue dot, a fragile oasis of life in an unimaginably vast and mostly empty universe. Yet, from that tiny dot, we conceived a mission to touch the infinite, to send a piece of our world billions of miles beyond our own star. This act of audacious curiosity is what truly defines us. It speaks to a spirit that refuses to be bound by our physical limitations, a burning need to see what lies just beyond the horizon, even when that horizon is the edge of the solar system itself. Voyager's journey from its triumphant planetary tours to its enigmatic final whisper beautifully captures the entire human experience in microcosm. It is a story of brilliant success where we used our intellect to solve impossible problems and reveal wonders we had only dreamed of. It is also a story of humbling mystery where the universe gently reminded us that for all our knowledge, we have only just begun to scratch the surface of its deepest secrets. This is not a failure, but the ultimate inspiration. The fact that our oldest emissary to the stars could still surprise us is a gift. It confirms that the universe is not a static museum to be fully catalogued, but a dynamic, living puzzle that will continue to challenge and enthrall generations to come. The mission teaches us that the goal of exploration is not to arrive at all the answers, but to continually find better and more fascinating questions. Ultimately, the Golden Record may be Voyager's most enduring legacy, long after its final scientific readings have been analyzed and debated. That collection of sounds, images, and music is a snapshot of a civilization brave enough to hope. It is a message cast into the cosmic ocean with no guarantee of a recipient, sent on a journey that will last long after our civilization, our languages, and even our planet have been transformed by time. It represents our best selves, our art, our compassion, our joy, and our yearning for connection. The record and the probe that carries it is our declaration that we were here, that we thought it was beautiful, and that we wanted to share that beauty with anyone else who might be listening. In the face of the unknown, we chose not to hide in fear, but to reach out with an open hand and a song. That act of hope echoing across the light years is perhaps our greatest achievement of all. From its fiery launch in 1977 to its final, frantic date, a dump from the edge of interstellar space, Voyager 1's journey stands as a monumental testament to human curiosity and ingenuity. It began as an ambitious mission to reveal the secrets of our solar system's giant planets, gifting us with breathtaking first glimpses of Jupiter's swirling storms and Saturn's intricate rings. It transformed into an epic voyage of pure discovery, becoming the first human-made object to cross the threshold into the space between the stars, a silent pioneer mapping the final frontier of our sun's influence. For 45 years, its steady signal was a constant heartbeat from the void, a reassurance that we could reach into the cosmos and touch it. And in its final act, it delivered its most profound gift, not an answer, but a magnificent, enduring question. This final, puzzling transmission ensures that Voyager's legacy is far greater than the sum of its discoveries. It is a permanent reminder that the universe is not a puzzle to be solved, but a mystery to be embraced. The greatest explorations do not end with a period, but with an ellipsis, inviting us to look deeper, think bigger, and dream wilder. That faint whisper of an anti-gravity anomaly, a force that seemingly defies the very laws of physics, is a beacon pointing toward the next great frontier of human understanding. It proves that no matter how much we learn, the cosmos will always hold surprises in reserve, ready to humble us and spark the next revolution in thought. So, as Voyager continues its eternal, silent drift among the stars, carrying our golden record of greetings and songs into the galactic future, we are left with its final hour echoing in our minds. Was it a natural phenomenon beyond our current comprehension? A complex interaction of plasma and magnetic fields at the edge of our solar bubble? Or could it have been something even more extraordinary, a brush with the invisible fabric of dark matter, a ripple in the quantum vacuum, or perhaps something our science has not even yet conceived? The beauty lies in the not knowing. This mystery is an invitation to wonder, a shared question for all of humanity to ponder. We want to hear what you think. After this incredible journey through the facts and the theories, what is your take on Voyager's final message? Do you believe there's a conventional explanation waiting to be found, or do you think the probe encountered something that will force us to rewrite the textbooks? Share your thoughts and your wildest speculations in the comments below. Let's continue this conversation and keep the spirit of exploration and curiosity alive.